friends. So this is Dr. P. Munaswamy, Professor, Department of ECE. Today we are going to discuss about the wideband frequency modulation, time domain description. So already in the last class we discussed about the narrowband frequency modulation. So that is the based on the beta value. If beta is less than unity, lesser than the unity, then modulation is named as narrowband frequency modulation. Whereas beta is greater than unity, then it is called a wideband frequency modulation. So that is based on the modulation index of the FM, that is beta value. It may be wideband, it may be narrowband. Now we can see the wideband frequency modulation, time domain description. So the FM we already have discussed the standard equation S of t equal to AC into cos 2 pi fct plus beta sin 2 pi fmt. So where theta equal to, we are going to assume 2 pi fct beta sin 2 pi fmt. So the FM wave can be expressed in terms of the complex envelope as S of t equal to real part of AC e power j theta. So AC is the magnitude of the model carrier signal, and e power j theta is the envelope of this complex wave. So S of t equal to real part of AC e power j 2 pi fct plus beta sin 2 pi fmt. So where S of t equal to, it can be rewritten as real part of e power j 2 pi fct s cap of t. So s cap of t is a periodic time function with a fundamental frequency equal to Fm. So this can be expressed as using the complex Fourier series as s cap of t equal to n equal to minus infinity to infinity Cn e power j 2 pi n of fmt. So this is the standard expression for this in terms of the complex form. So where Cn is a complex Fourier coefficient given by, so Cn equal to Fm integral minus 1 by 2 Fm to 1 by 2 Fm s cap of t e power minus j 2 pi n of mt into dt. Substituting this equation 3 in 5, we'll get the Cn equal to Fm integral minus 1 by 2 Fm 1 by 2 pi Fm AC e power j beta sin 2 pi fmt e power minus j 2 pi n fmt dt. So by substituting the value of Cn in the above equation, substituting the equation 3 in equation 5, so that means we are going to substituting the value of s cap of t. So remaining will be the same. So where Cn equal to AC Jn beta. So Jn beta, so that is here we are going to consider the Bessel function based on the modulation index. Because of it is a wideband frequency modulation, the beta value greater than 1. So we are going to get the infinity number of sidebands. So whereas narrowband frequency modulation, so beta value less than unity, there we are going to get the 2 sidebands only, upper sideband as well as lower sideband. Whereas coming to the wideband frequency modulation, beta is greater than 1. So that we are going to theoretically, we are going to get the infinite number of sidebands. So that we are going to find the Bessel function values in terms of Jn. So Jn beta equal to 1 by 2 pi integral minus pi to pi e power j beta sin x minus nx into dx. Where Jn beta is the Bessel function of the first kind, nth order with the argument of beta. So based on the value of this beta, so there are several types of the Bessel functions. So here for this case wideband frequency modulation, we are going to consider the first kind of Bessel functions. So substituting equation 7 in 4, so s cap of t equal to sigma n equal to minus infinity to infinity Cn e power j 2 pi n of fmt, where s cap of t equal to n equal to minus infinity to infinity AC Jn beta e power j 2 pi n fmt 8. By substituting the equation 8 in 2, so finally we are going to obtain what is the s of t value. So real time s of t equal to real part of AC sigma n equal to minus infinity to infinity Jn beta e power j 2 pi fc plus n fm into t. Similarly, we can obtain the other form s of t equal to AC sigma n equal to minus infinity to infinity Jn beta cos 2 pi fc plus n fm into t. So giving the values for n between minus infinity infinity plus infinity, so we'll get the infinite number of Bessel functions. S of t equal to AC j naught beta cos 2 pi fct plus j1 beta cos 2 pi fc plus fmt. So minus cos 2 pi fc minus fmt plus j2 beta cos 2 pi fc plus 2 fmt. So it will be going on until the cos 2 pi fc minus 3 fmt. So based on the expansion of these Bessel functions, you can see so j1, j2, j3 until the infinity functions. So we'll get the Bessel function coefficients, the values. So the Bessel function j0 to jn will depends upon the signal strength of the sidebands. So theoretically, because of the wideband frequency modulation, so the beta value is greater than 1, so that we are going to get the sidebands of infinity, which are located fc plus or minus fm, fc plus or minus 3fm, fc plus or minus 2fm. It will be going on until the fc plus or minus 2n-fm. So that means, so based on the n value, the sidebands is increasing towards the infinity side. So based on the strength of the signal, Bessel function strength, you can also truncate these functions by the law known as a Carson rule. So by the help of the Carson rule, we can define the truncated bandwidth of the FM. So that according to that, we are going to define the limited bandwidth from the infinite bandwidth. So you can see the Bessel functions, the bandwidth expansion. So the first one is the carrier function. So plus fm will get the first sideband, plus 2fm second sideband, plus 3fm. It will be going on until the n functions, nfm. So that coming to the wideband frequency modulation, so beta value is greater than 1, so that we are getting the infinite number of sidebands. So these infinite number of sidebands can be truncated by the strength of the Bessel functions. So you can see the Bessel functions values. So highest j0 of beta will give the max unity value. From this onwards, j1 beta, j2, j3, jn will be decreasing the value of the jn beta. So based on the signal strength, these values of the Bessel function j0 to jn, you can truncate the infinite bandwidth to the limit of the finite bandwidth. So that is the main advantage of the Bessel functions. So you can compare the both narrow band and wide band. So in case of the narrow band, beta value is less than 1. So the bandwidth requirement for the narrow band is similar to AM bandwidth. So there both cases we are going to have the two sidebands, upper sideband as well as the lower sideband. So the bandwidth requirement is 2fm only. So whereas coming to the wideband FM frequency modulation, so there beta value greater than 1, it is infinity, so that it can truncate, increases to infinity value of the sidebands. So based on the Bessel functions, the first kind of Bessel functions, we can truncate to the finite value, and also you can use the law of Carson rule for truncating the bandwidth. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.